Modern systemic financial risk operates in hidden networks. A localized default in one sector immediately pressures interconnected liabilities across the globe. To calculate this risk, the financial industry relies on linear regression, logistic modeling, and additive decision trees. These traditional formulas dominate the sector because they prioritize white box explainability. This allows regulators to trace exactly how every input impacts a final credit score. Deep learning architectures, including MLPs, CNNs, and RNNs, are built to identify complex patterns that these traditional models often miss. This diagram illustrates the core tension. Machine learning operates as a black box, contrasting with the clear inferential statistics regulators prefer. In this overlap, engineers face a choice: adhere to white box logic or use the black box to detect nonlinear threats. To justify using deep learning in high-stakes finance, we have to mathematically deconstruct exactly why standard models fail at high levels of complexity. The black box provides the structural capacity required to process reality as it actually exists, rather than as a simplified formula. The bridge from traditional modeling to neural networks starts with the bedrock linear equation, y equals a plus b1x1 plus b2x2. This schematic maps that linear logic directly onto the foundational unit of deep learning, the single-layer perceptron. Multiple explanatory variables act as inputs on the left, are multiplied by specific weights, and feed into a central summation node to produce an output. An artificial neural network, like a multi-layer perceptron, is simply a massive, layered duplication of this exact node structure. But this standard architecture has an absolute structural limitation. It requires input data to be formatted as a one-dimensional array. Watch what happens when a multi-dimensional data structure is forced into this architecture. The system slices the grid apart, stacking the values vertically into a single column. Variables originally adjacent in two-dimensional space are now mathematically isolated in the one-dimensional sequence. This forced flattening destroys the spatial geometry and the structural relationships inherent to the original data. Feeding multidimensional risk data into a standard one-dimensional neural network risks losing critical signals and causing the model to overfit on noise. The convolutional neural network architecture was developed as the direct answer to this one-dimensional bottleneck. Its primary advantage is structural. A CNN ingests data without destroying its multidimensional topology. It achieves this using the convolution operation, which deploys a mathematical sliding window, or filter, across the data. Instead of analyzing the entire dataset at once, the algorithm applies small mathematical filters across localized sections of the geometry. By restricting the analysis to local clusters, the system prevents the catastrophic parameter explosion that ruins standard flat networks. Because the window moves across the data sequentially, the algorithm inherently maps the spatial relationships of the inputs. Conceptually, it operates similarly to principal component analysis, but applies the logic spatially. Principal component analysis is a statistical technique that reduces the dimensionality of a dataset while minimizing information loss. Convolutional networks do not process isolated data points. They mathematically process the context surrounding those points. To see exactly how an algorithm transitions from processing blind numerical inputs to identifying a geometric shape, we have to look at a concrete calculation. Here, we see a raw data matrix composed of numerical values, representing localized pixel intensities. Buried within the noise, the sequence of sixes forms the distinct shape of the number 4. The algorithm cannot visually see the number 4. It must deduce the shape using localized rules. This active extraction process begins as mathematical filters scan the raw matrix for distinct geometric traits. Rule 1 of the convolution: the filter specifically scans the localized data for intersecting linear functions. Rule 2: the filter further isolates lines that connect at acute angles of 90 degrees or less. When these specific mathematical conditions are met by multiple intersecting functions within the window, the local shape is verified. The algorithm discards the exact coordinate positions of the pixels, retaining only the verified structural traits. This entire extraction phase outputs what is called a feature map. A feature map is a two-dimensional array that stores the specific geometric features detected by the convolution filter. The feature map acts as a highly compressed, abstracted representation of the core structural patterns found in the data. By isolating geometry from absolute position, the network achieves pattern recognition that is invariant to shifts, distortions, or scale. There is a critical misconception about this process. The convolution phase and the resulting feature map do not actually make the final prediction. The next step is feeding the abstracted feature map directly into the standard neural network layer. This works now because the spatial context has already been mathematically extracted and compressed. Flattening the feature map no longer destroys the critical topology. The fully connected layer applies standard supervised weights to this distilled geometry to execute the final classification, confirming this is a 4. A convolutional network is a hybrid system utilizing two distinct branches of machine learning. This chart categorizes the landscape of AI algorithms into unsupervised and supervised logic. The convolution phase acts as unsupervised dimensionality reduction, finding hidden structures without a labeled target. The dense network phase acts as supervised classification, anchoring those patterns to a final prediction. This two-step architecture, spatial extraction followed by linear classification, gives deep learning a significant advantage over rigid, single-step additive models. This brings us back to the financial risk industry's regulatory preference for one-dimensional interpretable scorecards. The most dangerous modern systemic risks, market contagion, dynamic fraud rings, and supply chain cascades, are not isolated variables. These threats are multidimensional events. They mandate topology-preserving algorithms to be detected accurately. It is true that the exact weights deep inside a convolutional neural network will always remain a regulatory black box. However, the mathematical mechanics of how they extract feature maps and preserve structural relationships are completely logical and demonstrable. For quantitative analysts and risk engineers, mastering this architecture provides a structural lens capable of mapping the complexities of modern risk.